Yep.
Okay, so we're going to talk about diffraction, and we're going to have a look and see if we can make the light bend by shining it past an edge that's kind of like as in the order of the same size as the length of the wave. Do you want to get the lights?
The video is very not good now. Oh, never mind it.
Yeah.
No, that's okay. That's not working.
Do you want to rotate the video around to look at the whiteboard?
Yeah.
What we can see on the whiteboard there is just the dot from the laser, and we can move that dot left and right. But as we move it to the right, eventually it's going to nudge into the scalpel, and look what happens as it hits the edge of the scalpel. See how it spreads out, stretches out, and what we are seeing is that there's that what was a dot of light has now become like twisted out to the right. So that light is bending around the scalpel blade as it passes the scalpel blade. Now what we need is a volunteer to give us a hair, please.
I'll give you a hair.
Give us a hair.
Why does mine not work? Oh, maybe talking about the hair.
And so, check out what happens. Oh God, there's like so many hairs here now. Out of control. Check out what happens as we let that laser light go past Imogen's hair. What do you see happening on the board there? It's spread out, but it's done more than just spread out. Check it out. What's it done?
Oh, there's gaps in it.
It's done brighty, darky kinds of things. And so what we're seeing happening is that there's light. It's going around both sides of the hair that we've hung off the clamping thing here. And so the light that goes around one side of the hair is meeting up with the light that goes around the other side of the hair. This is one of those really weird wave phenomena, that the light's actually interfering. And so by interfering, sometimes the light interferes to make dark patches, and sometimes it interferes to make bright patches. And so you can see not only has the hair spread out the light to the left and to the right, but it's also spread it out, leaving behind bright, dark, bright, dark, bright, dark. See how that's happening on the board? So that's because as the light goes past the hair, it's bending around it to the left and to the right. It's going around an obstacle. And so what we're seeing is diffraction, which means the bending of light as it passes either around an obstacle or through it. So diffraction is the bending of light or another wave as it passes either through a gap or around an obstacle. So the difference between diffraction and refraction is that refraction happens when the light or the wave goes from one medium to another medium, whereas the diffraction, it's always in the same medium, but it's passing around an obstacle or through a gap. So if we were going to draw this, that could be our obstacle, and we could draw our waves, just thinking about these lines as being the wave fronts, like the white crest of the wave, if it's a water wave. And so we've got those wave fronts coming along. What's going to happen to the bottom part of that wave front there as it hits that barrier? It's going to reflect off, And so this bit of wave here is going to undergo reflection. So what we're interested in this piece at the top here, this bit of wave at the top doesn't know anything about that obstacle down there that bit of the wave is going around. So this piece of wave just keeps going. Anyway, what we're interested in is this bottom section of the wave here that passes around the obstacle. So it passes by this obstacle, and then it suddenly finds itself free to move. And so the form it takes is kind of like if we just drop a pebble in the water, the waves ripple out from that and concentric circles, it's that same concentric circle pattern that we get. And so what we've seen is that just the piece of wave that's glanced off the edge there, that bit of wave there has changed direction. And so now we've got bits of the wave travelling down as well as across, even though the original wave was only travelling across. So that's what diffraction around an obstacle might look like. What about through a gap, like a doorway?
Then it would end up being like a semicircle on the outside.
Yeah, so our waves here, I'm trying to make the wavelength round about equal to the gap here. And so then the piece that comes out forms this beautiful concentric circle pattern. Kind of like that is what we're looking for. And so it doesn't ever quite diffract through 180 degrees, like it doesn't ever quite make it that it's travelling along parallel to the edge of the obstacle, but it can get quite close to that. So when the wavelength is pretty similar to the gap, then we get this beautiful concentric circle pattern. If the wavelength is much different, like we could make it.
Yeah.
If we had the gap really small compared to the wavelength, we just get tiny little bit of wave energy transferred through, hardly anything. So that, and if we make the slit really big compared to the wavelength, we're going to get like a little bit happening at the edge, but most of our wave energy is just going to carry on straight ahead without any noticeable diffraction. So what we're seeing here is that for diffraction, to get good diffraction, it's really important that the size of the wave has to be kind of similar to the size of the obstacle. That's why we can hear someone talking through a doorway, but we can't see them, because when we talk, the waves we're producing are kind of in the order of about 1 metre long, and the light that's coming off us is in the order of like hundreds of nanometers long, and so the door is much bigger than hundreds of nanometers. The light doesn't go around the corner, but the door is around about the same length as a sound wave, in the order of about meters, and so sound waves can quite happily diffract through a doorway. We can hear someone even though we can't see them.
Okay.